Hi, my name is Samuel Ripley, and today I will be giving a presentation on the math of Mersenne primes. I came across this topic when I was looking through a book that I have on Mersenne primes. I had a section on Mersenne primes that really interested me. In this presentation, I will first give an overview of prime numbers to kind of just set the groundwork for what I'm going to cover. Then I will give a brief overview and history of Mersenne primes specifically, and introduce their defining equation. I will also go over how they relate to other number groups, and then consider some areas of its uncertainty with Mersenne primes. I will then present my own research, calculations, and results, and see how they compare with already existing knowledge and conjectures about Mersenne primes. Finally, I will wrap up by summarizing my results, conclusions, and findings, and discussing how they might be relevant or significant to other related mathematical topics. So, what are prime numbers? Well, a prime number is an integer greater than 1 whose only divisors are 1 and itself. For example, the first 7 primes are 2, 3, 5, 7, 11, and 11, 13, and 17. Something really neat about prime numbers is that they all share the same mathematical form. Every prime number except for 2 and 3 can be written in either the form 6n plus 1 or 6n minus 1, where n is some positive integer. Now, this might seem strange at first, but if you think about it, for a number to be considered prime, it cannot be divisible by either 2 or 3. And since 2 and 3 are consecutive, this means that every prime number must be offset by 1 from their product, which is 6. If offset by 2, then it's even. If offset by 3, then it's divisible by 3. And if it's offset by 4, then it's even again. And if it's offset by 5, then it's just offset by 1, but just using the inverse operation. So every prime number must take this form. However, this does not mean that for every positive integer n, there is a corresponding prime number. For example, for n equals 207, neither 6n plus 1 or 6n minus 1 is prime. So now that we have defined prime numbers, what exactly does it mean for a number to be a Mersenne prime? Well, a Mersenne prime is actually just a prime number that can be expressed as 2 to the power of another prime number minus 1. More formally, a prime number m is called a Mersenne prime if it can be written in the form m equals 2 to the power of p minus 1, where p is some prime greater than or equal to 2. The first 5 Mersenne primes are 3, 7, 31, 127, and 8191, and their corresponding primes are 2, 3, 5, 7, and 13. It should be apparent from this list that not all prime numbers can generate Mersenne primes. When a prime number is used in the Mersenne prime formula and the resulting number is not prime, then it is called a Mersenne number. Mersenne primes are special cases of Mersenne numbers, so all Mersenne primes are Mersenne numbers, but not necessarily all Mersenne numbers are Mersenne primes. The discovery of Mersenne primes actually began with an increased interest in finding perfect numbers, with Euclid, the Pythagoreans, and Mersenne himself all making contributions to arrive at the m equals 2 to the power of p minus 1 formula we have now. They were searching for a formula that could be used to find perfect numbers, and they actually ended up finding a formula that connects perfect numbers and Mersenne primes. To understand this formula, however, first we must understand exactly what a perfect number is. A number is a perfect number if it is equal to the sum of its proper positive divisors, not including itself. The first 4 numbers have been known since ancient times. These numbers are 6 with divisors 1, 2, and 3, because 1 times 2 times 3 equals 1 plus 2 plus 3. 28 with divisors 1, 2, 4, 7, and 14. 496 with these divisors, and 8128 with these divisors. Now that we know what a perfect number is, I will introduce the formula that relates Mersenne primes and perfect numbers. In the 4th century BC, Euclid showed that for every Mersenne prime m with its corresponding generating prime, p, 2 to the power of p minus 1 times 2 to the power of p minus 1 is an even perfect number. This can also be written in terms of Mersenne primes as m plus 1 over 2 times m. This theorem is known as the Euclid-Euler theorem because Leonhard Euler conclusively finished its proof in the 18th century. It can also be shown that Mersenne primes and even perfect numbers have a one-to-one correspondence. Before going over my own research, I would first like to discuss some areas of uncertainty with Mersenne primes. In fact, it is not even completely certain whether the list of Mersenne primes is infinite. However, there does seem to be a general consensus that there are probably an infinite number of Mersenne primes, and there are a few conjectures that attempt to prove this. The Lenstra-Pomerance-Wagstaff conjecture states that there are infinitely many Mersenne primes, and it conjectures that the number of Mersenne primes less than x is approximated by e to the power of gamma times natural log with base of 2 of natural log with base of 2 of x. Here gamma is Euler's constant, and it's numerically equal to approximately 0.577. This expression is proven to be fairly accurate for the first 40 Mersenne primes, but for Mersenne primes after that, it doesn't really predict the growth rate very accurately. There are a few different conjectures that try to address whether the list of Mersenne primes is infinite or finite, but there doesn't seem to be anything conclusive. So, now that we have a good understanding and background of Mersenne primes, I will delve a little deeper into my own research. We already know that every Mersenne prime must be of the form 6m plus or minus 1, where m is a positive integer, using m to differentiate from m, or from n, which we will use for regular primes, and the prime exponents for Mersenne numbers. However, to start simplifying the Mersenne prime equation and manipulating it, it would be simpler to first have a single distinct form that every Mersenne prime can take. So I'll prove by contradiction that every Mersenne prime is of the form 6m plus 1, where m is a positive integer, and cannot be of the form 6m minus 1. So first, assume that every Mersenne prime is of the form 6m minus 1. So if we substitute into the Mersenne prime equation, m equals 2 to the power of p minus 1, we get, substituting 6m, lowercase m, minus 1 for capital M, we get 6m minus 1 equals 2 to the power of p minus 1. Adding 1 to both sides, we now have the equality 6m equals 2 to the power of p. Now, 2 to the power of p by definition is p multiplied by 2 multiplied by itself p times. So for any value of p, 2 to the power of p will have a prime factorization consisting only of 2's. From this, we can conclude that 2 to the power of p cannot be divisible by 3, because its prime factorization breaks down into just 2's, and therefore cannot be equal in any case to 6m, which must always be divisible by 3. Therefore, no Mersenne prime m can be of the form 6m minus 1, and since every Mersenne prime m must be either of the form 6m plus 1 or 6m minus 1, we can conclude that every Mersenne prime must be of the form 6m plus 1, since it can't be of the form 6m minus 1. I have tested this conjecture, my conjecture, for Mersenne primes 1 to 12, and it holds true for each one except for Mersenne prime 3. This is because 3 is a factor of 6, so it cannot be divisible by 6m plus 1 or 6m minus 1. It's just too small. So now that we have narrowed down what the exact form of Mersenne primes must be, I can substitute it into the Mersenne prime equation. So starting with m equals 2 to the power of p minus 1, we can substitute 6m plus 1 for m and 6n plus or minus 1 for p. So this results in 6m minus 1 equals 2 to the power of the quantity 6n plus or minus 1 minus 1. Subtracting 1 from both sides and then dividing by 6, we get m equals 2 to the power of 6n plus or minus 1 minus 2 over 6. We can separate this equation into two equations by considering both cases, where p is a 6n plus 1 prime and a 6n minus 1 prime. For p as a 6n plus 1 prime, we get m equals 2 to the power of 6n plus 1 minus 2 over 6, which simplifies as m equals 2 times 2 to the power of 6n minus 2 over 6, which simplifies further as m equals 2 to the power of 6n plus 1 over 3. For p a 6n minus 1 prime, we get m equals 2 to the power of 6n minus 2 over 6, which becomes m equals 2 to the power of 6n over 2 minus 2, and that whole quantity over... m equals 2 to the power of 6n minus 4, and that whole quantity over 12. I plugged in values of n for both the case 1 equation and the case 2 equation to find the m values, and then used those m values in turn to see if they produced Mersenne primes, and used two Excel spreadsheets, one for each case, to record my results and also help with some computations. Here is a spreadsheet of the first formula, and here's a spreadsheet for the second formula. Note that between them they cover all of the Mersenne numbers, and many of the n values produce Mersenne primes. They also don't miss a single Mersenne prime, and they shouldn't because of how the formula was derived using the definitions of prime numbers. Something that I also noticed with regards to the form of Mersenne primes is that every Mersenne prime can be expressed as the sum of numbers such that each number is double the previous number. So, for example, 7, which is a Mersenne prime, equals 1 plus 2 plus 4. 31 is 1 plus 2 plus 4 plus 8 plus 16. And 127 is 1, 2, 4, 8, 16, 32, and 64. And this holds for every Mersenne prime. Another interesting property that Mersenne primes have is that they consist only of ones when written in binary. For instance, 3, 7, 31, and 127 can be written respectively in binary as 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then 7 ones. The number of ones is actually equal to the prime exponent that generates the Mersenne prime. So, to summarize, in my research, I first proved that all Mersenne primes are of the form 6m plus 1, and then I tested and verified this conclusion. I then used this and the fact that all primes are of the form 6n minus 1 or 6n plus 1 to substitute into the Mersenne primes equation, and then simplified it into two separate equations. I then used these equations to generate Mersenne numbers and Mersenne primes, and then tested them and recorded my results using Excel. One way that my results could possibly be useful is in the search for Mersenne primes. Using the formulas that I found, it is possible just to plug in positive integer values of n, and they always produce Mersenne numbers, and then these numbers can be tested to see if they are Mersenne primes. This could be particularly useful for computer algorithms because of their iterative nature. For instance, all a computer has to do to find Mersenne numbers using this formula is to plug in values of 1, 2, and 3, and just counting all the way up and so on. And they will always produce Mersenne numbers in one of the formulas. So if not one, then the other, and it's always not alternating, but it's always one or the other, and never both and never neither. Well, this wraps up my presentation. I think that Mersenne primes and all their properties are really neat, and I just really enjoyed learning about them and using different equations and proofs to see what I could come up with. So thank you for watching, and God bless.